Hello, and welcome to Cozy Astrophysics with me, Paige. Tonight's topic will be gravitational waves, which is a relatively new and exciting area of research pertaining to massive body mergers. Gravitational waves are technically produced by any asymmetrically rotating body, although we can only detect gravitational waves produced by really massive bodies. They propagate through space similarly to electromagnetic waves, requiring no medium to travel. These waves dilate space itself, contracting and dilating the curvature of space-time as they move. General relativity states that the universal speed limit is the speed limit of light, which is 3 × 10⁸ meters per second. This is also the speed at which gravitational waves transmit. It means that gravitational attraction is not immediate, unlike Newton's law of gravitational attraction, which does not take into account time. When observing bodies with a lot of mass, the laws of physics start to change, and we can no longer rely on classical mechanics. So we have to use general relativity to start analyzing these objects. In fact, Albert Einstein mentions the idea of gravitational waves in his 1916 theory of general relativity, although Oliver Heaviside first proposed it in 1893. Gravitational waves are produced by rotating objects with non-spherical symmetry. An example would be a dumbbell rotating where the axis of rotation is offset from the center of mass. The same could be said for any orbiting body with a non-circular orbit, or orbiting bodies where they vary in mass. The Sun and the Earth produce gravitational waves, but not ones nearly strong enough to be detected by us with our current equipment. The first indirect evidence of gravitational waves was back in 1974, where an observation began over many years of the Hulse-Taylor binary pulsar. It was named after the scientists Russell Allen Hulse and Joseph Houghton Taylor Jr., who received a Nobel Prize for the discovery later in 1993. The binary consisted of a pulsar and a neutron star spiraling towards each other. The degradation of the orbit was observed over nearly 20 years, and the decay of the orbit matched predictions of energy lost to gravitational waves. Later, in 2015, the first direct evidence for gravitational waves was found by the Laser Interferometer Gravitational Wave Observatory, or LIGO. This event was the result of two massive black holes merging. The paper was published in 2016 and was surprisingly shorter than I expected. If you get the chance, it's a really good read. The binary was named GW150914, consisting of one body of 36 solar masses and another of 29 solar masses. After the merger, the final body had a mass of 62 solar masses. If you add those up, you might notice that those numbers don't really make any sense, and that's because about 3 solar masses were converted to pure gravitational energy, sending gravitational waves out through the universe. In the span of 200 milliseconds, the frequency of the detected gravitational waves increased from 35 to 150 hertz, meaning that the waves sped up at an incredible rate. LIGO measures gravitational waves using a system of lasers and beam splitters. The mechanism works by splitting the beams and refracting them in orthogonal directions, sending each a distance of 4 kilometers, reflecting them back, and then recombining them before sending them into a photodetector. As a strong gravitational wave hits the system, the beams are stretched and contracted depending on the phase of the incoming waves. The beams are then altered as they recombine with each other, going in and out of phase as they are affected by the gravitational waves. The differences between the phases is measured as length dilation. The LIGO site is equipped with devices to monitor any exterior influences, including seismometers, magnetometers, and cosmic ray detectors. Despite all possible outside influence, it was determined that none had a significant effect on the system during the main burst of gravitational waves observed. This discovery had major significance, as it changes the way we think about space-time and provides tools to look farther back into the universe's history. Gravitational waves are unaffected when moving through clouds of gas that obstruct certain frequencies of electromagnetic radiation. Gravitational radiation is effectively a new method of observational astronomy, to be used in tandem with our methods already established for electromagnetic radiation. Unfortunately, detecting gravitational waves is very difficult and requires very large observatories to accomplish. However, some exciting new projects are in development to build space observatories, like the proposed Laser Interferometer Space Antenna, or LISA, a space telescope planned to have 3 laser segments, each 2.5 million kilometers long. An observatory of this magnitude would allow for more precise measurements, given how minuscule the effects of gravitational waves on our current equipment is. I am fascinated by gravitational waves. They are so alien to how we know our universe to work. If there's one thing I've learned from taking astronomy classes in college, is you have to unlearn everything you think you know. It was my pleasure to have you, and I hope you learned something new tonight. Bye!